Oh, hello, my dear friends. Welcome to a new video. Today, we're going to solve the maximum depth of a binary tree on LeetCode. So let's get started. So as an input, we will have a binary tree, and our goal is to find its maximum depth. The maximum depth is the number of nodes going through the longest path on the binary tree. For example, the longest path in this tree is this one, and we have 1, 2, 3. So we have 3 nodes, hence the maximum depth is 3. We had also this path, but that's okay, it doesn't matter. Okay, the maximum depth is 3 anyways. Okay, so let's see this example. The longest path here is this one, and this one too. So the maximum depth here is 3. In order to solve this problem, we have 2 approaches. We have an iterative approach and a recursive approach. Let's start with the recursive approach. If I want to calculate the maximum depth of this tree by thinking with dividing the problem into different subproblems. So first of all, I need to know the maximum depth of this left subtree and the maximum depth of this right subtree. So if I know the maximum depth here and the maximum depth here, and I want to know the global and the total maximum depth, I just need to compare the depth of these 2 subtrees, take the maximum and add 1 to it. That's it. That's so simple. I'm going to repeat again so that it sticks in your mind. I need to, if I have the maximum depth of the left subtree and the maximum depth of the right subtree, and I want the global and the total maximum depth, okay, I just need to take the biggest of the 2 and then add 1 to it because we have a root here. Okay, we have an element here. That's why we need to add 1. Let's translate that into code. So first of all, I need the depth of the left subtree. So left depth. I'm going to use the max depth function with the root.left. I'm going to do the same thing here. Right. And here, right. Okay. And I need to return math.max left depth and right depth. And I need to add 1 to it. And of course, I must not forget my initial condition is if root is null, I need to return 0. Okay, I'm going to run the code. It works. I'm going to submit the code, and it works perfect. Now let's see the iterative approach. For the iterative approach, we're going to need and we're going to need a queue. Okay, and we're going to try to traverse our binary tree by level. Okay, so we're going to traverse these elements, then these elements, then these elements, and we're going to use a queue for that. So first thing, I'm going to put my root into the queue. Okay, perfect. Then I'm going to pop that element. Okay, now I have 2, so I'm going to add the depth. I'm going to add 1 to the depth, so this time it's going to equal to 1. It's going to be initialized to 0. Okay, now I have my 2. Then I'm going to add the left of 2. I'm going to check if it's not null. It's not null, so I can add it. And then the right. Okay, cool. Now I'm going to the next level. Okay, so, and as you can see here, at all times, I will have only the elements on the same level on my queue. Okay. Now I need to add again to the depth. I need to add 1. So now I'm in the second level. Okay. I'm going to pop again all these elements. I have 3, and I have 4. And now I'm going to add the left and the right of 3 and the left and the right of 4. So 3 is 5, 6, but 4 has nothing. And again, in our queue, we have the elements of this tree, but that are on the same level. Okay, I'm going to remove this. Now in the next iteration, I'm going to add to the depth, I'm going to add 1, so now 3. I'm going to pop all these elements, 5 and 6. Okay, I'm going to try to add the left and the right, but this time I have nothing. So I'm not going to add anything to the queue. Now there is nothing into the queue, so I can stop. And as you can see, the depth is 3. And that's what I wanted. Perfect. Now let's translate that into code. Okay. So first of all, I will need a depth equal to 0. I'm going to return it at the end. Okay. And I will also need a queue of 3 nodes, array list, and now I can go through my loop. I need to make sure, before that, we need to initialize our queue with 1 element, that is the root. Then I need to check if the queue is not empty. If it's not empty, I'm gonna increment my depth. That means that we are in the first level, okay, and so on and so forth. Then I'm going to calculate the current size of my queue so that I go through all the elements of the queue at this point, so that I can remove all the elements at the same level and add one more time the elements of the next level to the queue. So that's what I'm going to do. I'm going to add those elements. So E inferior to N, E++. I'm going to have a tree node called current, where I'm going to poll the first element of the queue, and I'm going to check the left of the current is different from null, and if that's the case, I can add it to the queue. And for the right too, okay. Cool. I think that's it. You can write out the code, new array list. Okay, not array list, linked list, sorry. New linked list. Okay, it works, we can submit. If current, therefore I current qpol. Command line, okay. So we have an issue here. Current dot left, tree node, qpol. Okay, actually maybe we need to initialize it outside, and int n, I'm gonna put it here, queue size, and it's gonna work. Okay, not current. I can submit it. Okay, what mistake have I made? Queue.poll. Yes, I've made a mistake. I need to check if the root is different from null. If that's the case, I'm gonna return a 0. Because here, what I've made, the issue is that if the root is null, and I don't have this condition, I'm going to add into my queue a null value. So when I'm going to go here, then I'm going to poll the first element of the queue. I'm going to poll a null element. So when I'm going to try to check its left and check its right, it's not going to work. Okay, now I'm going to try to run the code. Doesn't work. Of course, equal to null. What an amateur. Submit. Okay, it works. The time complexity of this program is O of n, because we're going to loop through all the elements. So it's going to be for the recursive and the iterative one, O of n. And the space complexity for the recursive one is going to be O of n, because imagine that we had a tree like this. So we will have in the call stack our first call here, then the second call here, then the third call here, and so on. So this is the worst case scenario. So in the worst case scenario, we'll have n elements in our call stacks. That's why here we'll have also O of n time and space complexity at the same time. Okay, and then finally for the iterative version, so at each point in my queue, I will have the number of elements in the same level. Okay, and in a balanced tree, the maximum number of elements in the same level would be at the bottom, so the leaves. And the number of leaves is n plus 1 divided by 2. So it's O of n plus 1 divided by 2. So it's O of n. So overall, in both the iterative and the recursive approach, both of them would have O of n time complexity and O of n space complexity. So this is it. Thank you for watching. See you in the next video. Bye.